Let's say that we have a couple of Cisco Catalyst switches interconnected with more than one link. Here we have a couple of links. If a spanning tree protocol is in effect on these two links, traffic is only going to be flowing over one link to prevent a layer 2 topological loop. However, what we can do is configure something called an ether channel. An ether channel is going to logically bundle together multiple links, and this allows us to have higher bandwidth, higher throughput between our switches. We can also have some load balancing between those different connections, and if one link goes down, the other link can continue to carry traffic. So we have some redundancy built in. And from the perspective of spanning tree protocol, this logical bundle that we're going to call a port channel appears as a single port. So spanning tree protocol is not going to be blocking this. This ability to logically bundle together multiple physical links was originally called ether channel by Cisco. There's now an industry standard. It's the IEEE 802.3 AD standard, and we might want to use that standard if we're in a mixed vendor environment, but both approaches are very similar. There is one concept that is very misunderstood about ether channel. Let's clear that up right now. When many people hear that we can load balance across these multiple connections, they imagine that one packet's going to go over one link and the next packet's going to go over the next link and so on, doing a fairly even job of load balancing. However, that's probably not going to be the case. When we bundle together these physical links, we can specify or we can use a default load balancing algorithm. One approach is to use the destination IP address, and here's the way this works. In this example, we have 4 links bundled together, and we ask how many binary digits does it take to give us 4 possible combinations? Well, it takes 2, doesn't it? 2 binary digits have 4 possible combinations: 0, 0, 0, 1, 1, 0, and 1, 1. So what we can do in this case is we can look at the last 2 bits in a destination IP address, and based solely on binary bit positions, we can select which of these 4 links we're going to use. Alternately, we could say, let's make that decision based on a destination MAC address. Personally, I like to introduce a bit more randomness into this to try to spread things out a bit more evenly. I like to use something like a combination of source and destination IP addresses or MAC addresses. What happens is we take the source and destination IP or MAC address, depending on what we select, and we do a Boolean operation on those addresses. We do an exclusive OR on the last 2 bit positions in this case. That way we're considering not just the destination, but we're also considering the source. And just like we had load balancing algorithms that use the destination IP address and destination MAC address, we've also got algorithms that can use the source IP or the source MAC address. Let's imagine in this topology on screen that we're using a destination MAC address, and we've got 3 servers, maybe in a server farm, connected off of switch B. And to make this a bit more readable, I didn't put the full MAC addresses of those servers on screen, but let's imagine that the last hexadecimal digits in those MAC addresses are 1, 5, and D. If you take a look at the hex to binary conversion table, you see that a 1 in hex can be written in binary as 0001, a 5 in hex can be written as 0101 in binary, and a D in hex, that's 13 in decimal, but in binary it's 1101. Notice the last 2 bit positions, if you would. The last 2 bit positions are 01 for all of these different values. That means as we're communicating to these different servers, we're going to be using the same link. We're going to be using that single link that is forwarding traffic that's destined for a MAC address that ends in 01 as the last 2 binary digits. Many people have a false sense of assurance that they're getting equal load balancing across these links when maybe they're not. So I wanted to make sure you understood how load balancing can happen. And by the way, in this example, I've got 4 links, so we're using 2 binary bits to make this decision. What if I had 2 links? How many binary bits does it take to make 2 possible combinations? It takes 1 bit, doesn't it? It can be either a 0 or a 1. So if we had 2 links, and we were making our decision based on a destination MAC address, we would only be considering the last bit in that 48-bit MAC address. If we had 8 links interconnecting these switches, we ask how many binary bits do we need to have 8 possible combinations? It's 3. 3 binary bits can give us 8 combinations, so we would be looking at the last 3 bits of, for example, our destination MAC address.